Good morning. We are finally at that chapter everyone's been waiting for, maybe, I don't know. Anyway, we're in chapter 9. It's linear momentum. Momentum is one of those words, kind of like energy. Momentum is one of those words that we use very frequently, just everyday conversation. And of course, in physics, we're going to have a very specific definition as to what we mean by momentum. Now, it's linear momentum because it turns out there's also a rotational version of momentum that's kind of a separate thing. There's some relationship between the two. We'll see this in chapters 10, mostly 11. It's called angular momentum. Anyway, linear momentum, we've got an object here. It's moving at some speed, has a certain mass, and it has a certain velocity. And for us, that's what momentum is. It's going to be the mass of the object multiplied by its velocity. And we'll find out that that has a very important set of properties to it. The momentum is conserved the same way that energy was conserved. So it's kind of a new set of conservation rules that we want to familiarize ourselves with. Now, when you got a pool ball hitting another pool ball, and this one I'm not even sure of because it doesn't have any numbers written on it, but we've got what looks like a pool ball hitting another pool ball. There's more stuff going on. First of all, the pool balls are rotating, and that complicates things. So that's, again, not till chapters 10 and 11 when we start looking at rotation. So a better representation of what is purely linear momentum would this be some object moving, not rotating, coming in and then bumping into or colliding with or interacting with another object, and as a result, both objects change their motion. So in this picture, this object comes in, heads off at some angle. This object was at rest, and now it's heading off at some other angle. These collisions can be pretty complicated, so we want to start with the easier versions. We'll see what this momentum thing is all about and how it relates to these collisions. Here's a list of all the stuff we hope to do in the chapter. I'm going to move on to where we start looking at the definitions. So linear momentum is a vector quantity. So linear momentum, we use the obvious symbol P, right? If you were choosing a letter to represent momentum, I'm sure you would have picked the letter P. So this is no, I don't see a P in there. Anyway, this is momentum. It's the object's mass times its velocity. Now, since they're vectors, that means component for component, there's going to be an XYZ components of momentum, and there's going to be XYZ components of velocity, and they're going to line up. So the X momentum depends on the mass times the X velocity, and so forth. When we get to special relativity in physics 4C, we're going to find out that this is one of those formulas that's based on Newton's laws of motion, and that it's only an approximation. It's an approximation that works really, 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 really well, except when things are moving really fast. And so for us right now, this is going to work fine, but in physics 4C, we're going to come in and tweak that a little bit, what our definition of momentum is. Now, forces can be directly related to momentum. You know, we're used to thinking in terms of accelerations and forces and mass, but rather than using accelerations, we can write this in terms of dp dt, and we'll see examples of going back to this formula. And the story is that that's how Newton originally formulated the laws of motion, was using momentum rather than in terms of velocities and accelerations. So we'll come back and take a look at some of this stuff. Let's move on here. So here's a general momentum set of ideas. Let's say we have an object. It's got a mass. I set the mass at 1,000 kilograms. Here is a velocity. It's 30 meters per second. Maybe this is my 2004 Honda Civic. We're headed down the highway here. It's going to have kinetic energy. And I know that because we did chapter 7, we did chapter 8, and we're familiar with kinetic energy and what kinetic energy properties are like. Now, momentum has kind of the same feel because it depends on the mass and it depends on the velocity. Now again, once we get to special relativity, we're going to find out that in general, even objects without mass can have kinetic energy and momentum. And in particular, light. So light, which consists of particles we call photons, those photons have energy, it's kinetic energy, and they have momentum, even though they have no mass. So these formulas, again, these are for objects that have mass, and they're not moving super fast. Okay, they're not approaching speeds kind of at the order of magnitude of the speed of light. Okay, well, let's get back to the current kind of classical physics then. So we can calculate this object's momentum. It's m times v, and that would put it at 1,000 kilograms times 30 meters per second. Numerically, that gives us the number 30,000. So apparently this car has a momentum of 30,000 momentum units. Now, momentum units, we can see by the formula, would be kilograms times meters divided by seconds. Now, it turns out that this particular combination is interchangeable with newtons times seconds. And sometimes we prefer using newtons times seconds, other times we use kilograms meters per second. But that's the momentum of this car. Now, since momentum is a vector, if the car is going this direction versus this direction, we have to do something in the diagrams. We have to be able to keep track of directional information of the momentum. So a car going this way, and a car going this way, they don't have the same momentum. Even if they have the same v and the same m, it's not the same momentum. Now, kinetic energy is a scalar, so we don't have to keep track of the directional information. And the kinetic energy formula that we derived in the last chapter, 1/2 mv squared, plugging the numbers into that, it turns out that for this car that we've identified with these numbers, has a kinetic energy of 450,000, kilograms meters squared per second squared. Now those are joules. We don't have a unit like that for momentum. So if you guys have any suggestions, let me know. If you have suggestions for what we could use for units of momentum, in many ways it'd be very handy to have something, but nothing has really caught on and been universally accepted. And so, we're stuck with these combinations that we're going to be making use of. Whereas with energy, always get that converted over into joules. The joules units will be very clear that we're talking about energy. Now, I can't really do a comparison here. I can't say it has more kinetic energy than momentum because the units are different. Okay, if we define units differently, these numbers would come out different also. But there is kind of this connection between kinetic energy and momentum, and we'll see kinetic energy is going to show up in this chapter. We're going to be talking about kinetic energy. So here's the way it works. If I have a car, or an object, if I have an object with mass m, and there's a force acting on it, we're going to ignore all the other forces. We can start with Newton's laws of motion. Newton's laws of motion say that if there's a force acting on an object, and that's the net force, then I can take that force, divide it by the mass, and that will tell me how much acceleration I am going to have. Now, we've got that written here too. So this is kind of the momentum side. Let me come back over here. To derive what we mean by momentum, what I can do is I can take the acceleration then and say acceleration is dv dt. That's just kinematics. That's just keeping track of how the velocity is changing with respect to time. So I can set these two things equal to each other. Now if I cross multiply, if I bring an m to this side and the dt to the other, I'm going to get a formula that says m dv equals f dt. Now momentum is defined as m v, so we could write dp, a little change in momentum, would be equal to mass times dv a little change in velocity. Now the m dv that we came up with here is equal to f dt, so I can substitute that in, and look, the force tells us about how the momentum of an object is varying. So if I've got a force, I can directly relate that to the rate at which momentum is being transferred. Force is the momentum transfer rate. Now, how does kinetic energy figure in? And we did this derivation back in chapter 7, I want to say, maybe 8. But what we did is we showed that not only can acceleration be written as dv dt, but we can do this trick where we put a dx on top and a dx below, and yeah, those dx's and dt's and dv's, they can all just be moved around like variables. So what I've got is a dv dx times dx dt. Well, dx dt is v, so that becomes v. I switch places, so this is now v dv dx. So accelerations can also be written as v dv dx. Now that can be set equal to f over m. Now, back when we were looking at this formula, we said at this point, time is no longer in the formula. So I have the acceleration in terms of displacements and in terms of velocities. So the formulas we come up with are not explicitly going to show time. And so when we carry this out, if I do m dv, mv dv, if I bring the m to this side and bring the dx to the other side, so you can kind of do this row by row. Over with the time side, the momentum side of this, we had m dv, but here we have mv dv because of this extra factor of v. And then over here we have dx instead of dt. If we integrate these sides, what we can see is that this side will integrate out to be a 1/2 mv squared. This side over here, that's work. Okay, so what we're saying is that kinetic energies then are 1/2 mv squared. It comes from integrating this side. And little bits of kinetic energy are mv dv. And so a little boost in kinetic energy comes from a force acting over a distance, and that's work. Okay. So just a side-by-side comparison to see kind of the calculus basis for these. And then we can continue on. What we can say with momentum is I could integrate all of the variations that happen in momentum. If I add those all together, I'm going to get delta p. So if I add together all the momentum increases, for example, in an object, that'll give me a delta p. And that becomes the integral of f dt. Now, the comparison here was from the last chapters. If I add together all the dk's and set that equal to f dx and integrate both sides, what I'm going to end up with is that the kinetic energy increase or decrease is a result of, I can set that equal to forces integrated over distance. So this is called work, which I suggested made no sense. That's kind of a crazy term to use. So I think for momentum we need something that will be f dt with kind of a similarly confusing word. And so we call that impulse. So it's kind of funny. Impulse is the force integrated over time. And so, you know, I always think of impulse as I'm standing in line at the grocery store and there's a Snickers bar there and I'm trying to decide if I want to get one or not. Anyway, we have impulse. Now, we also have a crazy letter to keep track of that. We use a capital J. Now, it's not a unit, so it's not joules, but we do use a capital J to represent impulse. And that is officially integrating over the force, acting on an object over time, the same way that work. Now, we spent a lot of time looking at work. We're not going to spend as much time looking at impulse, but from all the time we spent with work, you kind of get a feel for this. And then we said with work, we could actually use what we called a dot product. We introduced that and said that work could be expressed as the integration of forces times displacements, and to keep track of all three dimensions, we did a dot product. the formula for impulse, impulse is going to be a vector because force is a vector. So the vector signs here match up from left to right, whereas over here, the two vector quantities, we end up with a dot product and get a scalar. So at the end of the day, we said work was an energy transfer. Anytime work was being done on an object, energy was being transferred in. Similarly, this is impulse, and impulse is a momentum transfer. So again, I wanted to do a side-by-side comparison because, you know, we spent a fair amount of time developing the ideas of energy and kinetic energy, and now you can see there's kind of a similarity between kinetic energy and momentum. So a couple of other things to keep track of here. Because kinetic energy is a scalar, we can just add all the kinetic energies together. If I have a bunch of objects, I can just add all their kinetic energies together to find out what the total kinetic energy is. Let's imagine that we have a bunch of gas molecules. Maybe we have N, where N is a really large number, or not. But anyway, we have a collection of gas molecules here. How much kinetic energy is in all the gas molecules? Well, I just have to go through one by one and find out how much energy is in each one. So if molecule, if gas molecule 1 has kinetic energy 1, then I can add that to kinetic energy of molecule 2 and 3. I add that all together. Those are all positive quantities. They're all going to get added together. So the total kinetic energy in a collection of gas molecules is given by just the summation. We call that the thermal energy of the molecules, or we call it sometimes the internal energy. We'll delve into that more in Physics 4b. Now, momentum's a little different. How would I calculate the momentum of all these gas molecules? Momentum's a vector. So that means that, if one molecule has a momentum in this direction, another molecule has a direction in another direction, those are going to cancel when I add all the momentum together. So if I have a collection of gas molecules in a container, and the container's just sitting there on the table at rest, the total momentum is 0. Not because the molecules don't have momentum, but because momentum cancels out. I'm going to have equal amounts of molecular momentum towards the right as towards the left, as towards the back and the front and the up and the down. And when I add vectorially everything together, it's going to end up being 0. Something to keep in mind when we're looking at systems. All right, here's an example. We got a tennis player here. Tennis player, this tennis ball is coming in, and we're gonna wallop this tennis ball, and it leaves the racket. It says this person is serving the tennis ball, so it's starting kind of at rest, right? We're throwing this tennis ball up into the air, and it's almost at rest. Maybe it is at rest because the tennis player wants to hit it kind of at the top. And then they're going to hit this, and then it's going to pick up a lot of speed. Now, if it picks up speed, it's going to pick up momentum. So and we can calculate how much momentum. They've given us the mass. It says it's a 60-gram tennis ball. And they've also given us the force. Or they've given us not the force, but the time of contact. How much time is the tennis racket in contact with the tennis ball? So in this case, the momentum is being transferred very rapidly. And it turns out that when we have rapid collisions between objects, momentum can be very useful in solving information about what just happened. Now, it doesn't have to happen quickly, but in many of the examples, you'll see that happening. So here's the setup. Here's the tennis ball, 60 grams, 55 meters per second. How much momentum is that? And I can multiply m times v. That gives me 3.30 kilograms meters per second, or in Newton seconds, very same number. Now, what they wanted to find out was how much force did the tennis racket, with how much force did the tennis racket hit the tennis ball? What kind of a force did the tennis ball experience from this? Now, what we had done on some earlier slides, so I guess I can go through this quickly, is here is acceleration is force over mass. I can substitute in dv dt, bring the m over, slide the m in. I guess I don't have to slide it inside. That becomes dp. So dp dt is equal to f. dp is equal to f dt. We can integrate both sides. And it says that the momentum increase or decrease is going to be equal to the force integrated over the time when the force was acting. So an average number for that would come from here. We could start from here or here maybe and say the average force would be delta p over delta t. So the increase in momentum, 3.30 newtons times seconds, the time period over which this happened, they told us, was very short. So the way this works is, look, if I'm going to bring a tennis ball or an object up to some speed, I'm going to need to come up with some momentum. I'm going to need to transfer some momentum into that object. Now I could transfer the momentum slowly, or I could transfer the momentum rapidly in a very short time period. And in this case, because the time period is so short, transferring that momentum is going to require a really large force. So we've calculated here a force of 825 newtons. That's, on average, how much force was acting on that tennis ball. Now let's think about this. So here's the tennis ball, here's the racket coming in. When does the force begin? And the force begins as soon as contact is made. And then contact is maintained. Now, we've transferred a lot of momentum, so the ball is beginning to move away from the racket. And once they separate, that's it. Then there's no more force coming from the racket once the ball has separated. So that's an average value, but it doesn't tell us instant by instant what the force looked like. We'll see some examples of that later. Here's another example where momentum becomes really useful in solving problems of continuous flow of mass. So this person has their hose out, and they're not spraying the car, they just got a hose going in one direction, hitting one spot on the car. The water's coming out of the hose, running over, now it hits the car, and then it just runs down. So apparently what happens is, I've got the car wall here, and here comes the water, it hits, and then all of the momentum of the water is transferred out. So the water loses all of its momentum, and then the water just drops from gravitation. So the collision of the water running into the car, we could go in and do some momentum calculations on that. So it says that water is leaving the hose at a rate of 1.5 kilograms per second. That's 1.5 liters a second. Hey, if you're going to be using all that water, you got to spray it around the car and do this quickly. It's kind of like it's a leisurely activity here. 1.5 kilograms per second, and it's coming in with a speed of 20 meters per second. Now that's before it hits. It's coming in at 20 meters per second, and then it hits, and then the speed drops down to 0. So here's what it looks like. So here's that water. We have all the numbers. Okay, here's the speed coming in, and here is the mass rate, 1.5 kilograms per second, and so the force we can calculate this way. What we can do is we can say that F is equal to dp dt. Now in this case, if I take a little bit of the water, let's say I got a little bit of water, it's got a mass of dm. So dm represents a small amount of the water, and the momentum of that water coming in was dm times v. So each little piece of water has a momentum dv, dp. Now, what I can do then is I can take the dp and substitute this expression in, so I have v times dm dt. Now, the speed, once it hits, drops to 0. So I've kind of left off the 0 here, but that's an important part. We really have to know how the momentum is varying. And so it starts off with this much momentum, but then when it hits the car, all the momentum is gone. So all the momentum is being transferred out by this force. And we can calculate that force by taking dm dt and multiplying by v. So I'm multiplying these numbers together. Now, more generally, and I've got that here, so this is, did we get the final force number? Oh, we did, finally, here it is. Okay, so it comes up here, and the force we calculated for this picture was 30 newtons. But more generally, what we can do is say, look, if it bounces off, what if the water comes in at 20 meters per second, and there's enough force to completely stop the water, and then there has to be additional force to push the water off the car. So something hitting the water and bouncing back, hitting the car and bouncing back, actually is a bigger momentum change. That's going to require a bigger force. So the forces are going to be bigger. Just a reminder, this is a contact force. So the car is experiencing a force of 30 newtons, and the water is experiencing a force of 30 newtons. The 30 newtons on the water is enough to slow down the water that's coming in. So it's a steady force of 30 newtons, and it's continually slowing in water as it arrives. Now, 30 newtons in the other direction is pushing on the car. So the car, I don't know, maybe it's tipped up a little bit because of that 30 newtons. That's about, 6 pounds, 6 or 7 pounds of force. It's not much. And so that momentum goes into the car, and the car is attached to the planet, and the planet recoils a little bit, but not enough that you would notice it. It's useful in this example, solving for what's happening with the water. It's harder to take that 30 newtons and think about what impact it has on the car. In any case, if we are going to have something not just stop, but bounce back, that represents an even larger momentum change. That's going to require a larger force. How do we do the calculations? Well, by putting in a delta V, that then takes care of the difference in momentum from before and after. And so in this case, the delta V would be 30 meters per second, and that would mean that's a force of 45 newtons. So we have to look and see, it's going to depend on the elastic properties of whatever the collision is happening with. If, I don't know, if the car is springy or something, I don't know. You have to think about how the water could bounce off the car with a higher speed. Conservation of momentum. So we had started out saying that momentum is a conserved quantity. So what that means is, if I have these two objects and they run into each other, we can divide the collision. These are considered to be collisions. So object A and B are headed towards each other, and what we do is we write down all of their properties before the collision happens. So the before picture looks like this, and then here is the collision itself. Now, if it's like the last example, then the collision probably lasts for a very short time period, if it's like the tennis ball. So that could be happening for a very short time period, the collision itself, and then there's, then they separate. So here's before the collision, collision, after collision. If we go in and we add, using vector notation, MA times VA plus MB times VB, so that would mean I would take M times VA, which looks to be in the positive direction if we use a standard coordinate system, and then MB VB, where VB is negative using a standard coordinate system. I could add up the total amount of momentum. Now, because during the collision, contact forces are going to be equal and opposite forces, and they're going to last for the same amount of time. Object A is in contact with B for the very same amount of time that object B is in contact with object A. So they hit, they exert equal forces for equal amounts of time, they separate, and what our formulas for momentum are telling us then is that, formulas from here, they're telling us that there's going to be a momentum transfer. So object A does not have the same momentum as before. Object B does not have the same momentum. But if we add the momentum from before and the momentum after, we find out it's the same number. So, and when we go into the lab and we do these kind of measurements, we find out this prediction, because it's a prediction based on Newton's laws of motion. It works. We do find that momentum is conserved in these reactions or in these collisions that take place. So as they're saying here, conservation of momentum is a prediction. It can be derived from Newton's laws of motion. And a collision has to happen, for this to work, it has to be the case that we are able to isolate these objects. So as long as we can isolate these objects away from other objects or other forces during the time that the collision is taking place, this is going to work. But if other forces are involved, if there's other forces coming in from outside, that's going to affect these objects. Now, momentum still gets conserved. It just means we have to draw the picture bigger. If there are more forces that we have not accounted for, then maybe we need to bring other objects into the system of objects we're looking at. Here's a collision. So in this case, they didn't quite line up like this. They hit kind of, you know, off alignment, and as a result, here's before the collision, here is during the collision, and now they've actually shown the two forces, and they're in equal magnitude but opposite directions, and then they're gonna separate. Okay. So that's what these examples are going to look like. They're all going to be looking something like that. So if we do have more than two objects, what we can do is we can add together all of the momentum changes that are taking place and set those equal to all the forces. I don't know anywhere we're directly going to use that, but that's just a statement. Okay, so all the forces within the system cancel out, and then the remaining changes in momentum are going to be due to external forces. Again, I'm not sure if I think, we kind of talked about that already. So here it is, they're saying, this is it, the law of conservation of linear momentum. When the net external force of a system of objects is zero, so if we have a collection of objects, and we've been able to isolate those objects from outside forces that might be acting on them, then the momentum of the system remains constant. I guess this is closer to what I was saying. Total momentum of an isolated system of objects remains constant. All right, here's an example that is often used, and some of these are just a little hilarious. So here is a railroad car A, and here is a railroad car B, and this railroad car is at rest, has no velocity. This railroad car is going 24 meters per second. Now, just how fast is 24 meters per second? And you know, back early in the course, we did those calculations for every 10 meters per second. What was it? It was 22 miles an hour. So we're looking at this is probably 55 miles an hour. So they're going to extremes here. They're not having railroad cars just kind of bump into each other a bit. This is a major collision for sure. This is going 55 miles an hour, and it runs into another railroad car. And look, there's the after picture below, and there's no damage. So the two railroad cars successfully coupled, with one going 55 miles an hour. And then they're saying, okay, if momentum is conserved, then how fast would the railroad cars be moving after this collision takes place? And I can't stop thinking about this railroad car coming in at 55 miles an hour and there's no damage. Everything works perfectly. So they must have just an amazing coupling system right in here, right? With a bunch of cushions and springs and things, and to damp out the motion. Anyway, it could happen, but I think you'd have to engineer it very carefully to maybe. to have an object with that much mass come in and look, it's 10,000 kilograms each, and have a collision where they both survive and just head off. Okay, here's what the math looks like. So I guess we have to ignore reality here for a minute. So M1 and M2, M2 is at rest. M1 is coming in with velocity V0. That's my before, oh, it says before picture. Before picture, after picture. I didn't show the collision itself, but here the two masses are now just moving off together at the same velocity. So now if two objects stick together, we refer to that as an inelastic collision. In fact, it's totally inelastic in that when they come together, there's no separation velocity at all. This is totally inelastic. Now, totally inelastic collision problems are great because, look, there's really only one thing to solve for. There's only one final velocity. I don't have, two velocities to solve for, and I don't have different angles that the objects are coming out of the collision. Everything's moving together. So here's how momentum conservation works. I can take the momentum before. That would be the momentum here, which is m, v0. Remember, they both have the same m, and it's 10,000 kilograms. So m times v0 plus m times 0, that was the before momentum, needs to be equal to, now this is kind of like one object with mass 2m coming away at some velocity v. So if I cancel out the mass, the v0 then equals 2 times v. Flipping that around, the final velocity is 1/2 of the velocity of the object coming in. And you're thinking, oh, of course, 1/2, that makes sense because they were both the same mass. And so what's happened here is this came in with some amount of momentum. Ooh, well, how much momentum was it? And it looks like m times v0 is what? M times v0 is 240,000 kilogram meters per second. So this came in with that much momentum. And then what happened was the momentum transferred. Some of the momentum. So not all of it. Half of the momentum transferred to the other object. Now, once half the momentum has transferred, then they're both moving at the same speed. So they both have the same mass, and once half the momentum transfers, then they'll both have the same speed, and that's what's going on in the after picture. So there's enough symmetry here, the masses match, that it turned out that the final velocity is 1/2 the initial velocity. That would be 12. So that first railroad car comes in at 55 miles an hour, there's a collision, and they both move off happily at 27 meters per second, something, or 27 miles an hour, right? So before, let's take a look at this. The relative velocity before, at what speed did the two objects approach each other before the collision? And before the collision, the speed of approach was 24 meters per second. If I'm this object, I see that I'm coming up on this other one at 24 meters per second. If I'm this object, I look over and this one's coming in at 24 meters per second. That's a relative velocity. After the collision, the relative velocity is 0. That makes it totally inelastic. Now, here is the momentum transfer worked out. Now, to calculate the momentum transfer, I have to look at the two objects individually. So if I follow object 1 started out with momentum m1 v0, and it ended up with m1v. So I'll take the final momentum and subtract off the initial momentum. And that gives me a delta P1 of 10,000 kilograms, final velocity minus initial velocity. And it says the collision resulted in a loss of 12,000. It's 120, right? Okay, these have got to get bumped up by a factor of 10. Yeah, I've miscounted the zeros. Sorry about that. So this is going to be 12 times, not 1,000, but 12 times 10,000. This needs to be 120,000 Newton seconds. So initially, car 1 had 240,000 units of momentum. It lost 120,000 units of momentum, and that's indicated right here. Now, on this, for object 2, its final momentum, again, it's final momentum minus initial momentum. And the final momentum is m2v. Initially, it didn't have any momentum at all. So it picks up the 120,000 newtons times seconds. So it acquires the 120,000 newtons per second and heads off. So this concept of momentum transfer, they kind of hint at it in the book. I think there may be the homework problems that talk about it, but pay attention to that. That's something I really want to emphasize. I think that really helps keep track of this idea of momentum conservation in these problems. And I could easily ask about momentum transfer in one of the upcoming midterm, for example. All right, a little rocket science here. So what about a rocket? Here's a rocket sitting here in space, and it's apparently at rest with reference to the coordinate system that we've come up with. So in this reference frame, the rocket has no momentum, and then the engines are fired. What happens? And what's going to happen here is that the gases coming out the nozzle are going to have a lot of momentum. We come up with the most violent chemical reactions we can to serve as rocket fuel, and then that violent chemical reaction results, because of the shape of the combustion chamber and because of the nozzle where we've left an opening, then the only place where those rapidly moving gas molecules can move is out the back. And since we've directed the momentum of the exhaust coming out from the chemical reactions, that means that the momentum of the rocket will be equal and opposite. Momentum's conserved, and so what's happening is these two objects are pushing away from each other. The rocket is being pushed forward by the collisions with these gas molecules, and the gas molecules are being pushed back by the front of the combustion chamber. So the gas molecules hit the front of the combustion chamber, bounce backwards, and the combustion chamber and the rocket move forward. Rifle recoil is kind of the same thing here. We have, we have a bullet inside here. There's a chemical reaction. The bullet is the gas molecules in here expand. The gas expands very rapidly and pushes one piece of metal out. So that's a certain amount of momentum in one direction. That means that there will be a momentum in the opposite direction, a recoil momentum. And it could be significant. Here are the numbers for that. So what we're going to do is just treat that as two objects, object 1, object 2. Now in this case, the masses are very different, right? They're saying the bullet is 20 grams, the rifle is 5,000 grams, and then they're saying that the speed at which the bullet comes out is measured to be 620 meters per second. So that says that the combined momentum before the collision was 0. So the combined momentum after the collision, I guess this is more of an explosion than a collision, it needs to continue to be 0. And so m1 plus v1 times v1 plus m2 v2, they got to add up to be 0. That, with a little algebra, says that the velocity of the rifle then is given by this expression with the ratio of the masses. Now remember, the bullet's mass was really tiny, so the rifle's velocity is really small compared with the velocity of the rifle, but it's not 0. All right, and so yeah, so it's like 200 times different. So the mass of the rifle is 200 times greater, and so its speed is like 200, 250 times. I guess 250, huh? 250 times less. So, but that's significant, right? If you're holding the rifle and you're not expecting that, that could be a significant effect. All right, here's another, it's an interesting question. There's an empty sled sliding on frictionless ice. Susan drops vertically from a tree. When she lands, does the sled speed up, slow down, or keep the same speed? A little ways farther along, Susan rolls off sideways off the sled. What happens to the speed of the sled then? So let's take a look and see. So again, here's the sled. We'll call that M1. And here is the person dropping. We'll call her M2. And so what's happening here is the sled has a mass M1 and it has a momentum V naught, has a speed V naught. And so it's got a momentum of M1 times V naught. Well, that's the momentum in the x direction. So that's momentum in the x direction. Susan's falling from up above. Now, it's true that when Susan hits, she has a lot of momentum in this direction. But what happens to the downward momentum? And that downward momentum is transferred out. Because she hits the sled, that momentum transfers into the ground, transfers into the planet. And so that momentum is out of the picture. Now, Susan didn't bring any x momentum along, but she does bring mass. So what happens here is we can do the calculation entirely in terms of x momentum, momentum in the x direction. And we started with M1 V naught. And then once the two objects are stuck together, then we have M2 and M1. Well, they're going to be moving off at some speed. And so that's going to result in a slowdown. The sled will actually slow down. So that's kind of interesting. So where were the forces that caused the sled to slow down? And what happens is, when M2 first lands here, M2 is not moving forward. So M1 is moving forward, but M2 is not. If this is completely frictionless on the sled, then M2 stays here and M1 continues forward and M1 just slides off. But there's enough friction between these two that M12 falling onto M1 exerts a backwards frictional force. Meanwhile, M1 exerts a forward frictional force on M2 and brings M2 up to speed. So the sled exerts frictional forces on Susan and brings Susan up to speed, and so she is able to stay at the same velocity of the sled. So that's what's going on. Now, one of the features of using momentum conservation is we don't have to know the details of what happened during the collision. As long as we know initial information about mass and velocity, and we also know final information about mass and velocity, we don't have to know what happened here in the middle. So I know the initial mass and velocity, and again, we're looking in the x direction, and I can draw a picture of what's going on after the collision. I can take the x momentum before, set it equal to momentum 2. That's how fast the sled will be moving. Sled's going to slow down. Depending on how the masses compare, if M2 is much bigger, it'll slow down a lot. If M2 is much smaller than M1, it won't be as big of an effect. So that's how it's going to work. Now, what happens when Susan just rolls off the sled? You know, you're heading along, you know, really fast or whatever, and the snow here, I guess, is frictionless. We have to assume that. She rolls off. When she rolls off, she takes her momentum with her, right? If this sled's moving, you know, 10, 20 meters per second, and she rolls off, she is moving forward at 10 or 20 meters per second, okay? So she is going to carry that momentum with her. Now, is there a way she could not carry her momentum? She could push the sled forward as she falls off and give the try and transfer more momentum to the sled. But if she just passively rolls off to the side, that momentum is going to come off the sled. The sled is now going to pick up speed. It's going to be still traveling at the lower rate. Okay, so some of these momentum problems are kind of fun to think about. Where is the momentum? Where is it transferring? Here is that tennis racket problem again. Now we had gone through these formulas. So we had shown that we could keep track of this in terms of something we called impulse. And so here it is. Specifically, impulse looks a lot like work, right? Or there's a real similarity. For impulse, we're integrating the force over time. For work, we were integrating the force over displacements. Now, any changes that take place in momentum of an object can be related back to the impulse, some kind of an integration over time. Now, what's happening here, think of the tennis ball. When the tennis ball first hits, it's not immediately 800 newtons of force. It's going to take a little bit of time. So here is the moment of contact. And you know, the tennis ball and the racket are getting closer. Up, first contact, and then the force rises rapidly. It peaks, and here is the tennis ball coming off the tennis racket. So now it's beginning to separate more and more and more. There's less and less force. And finally, right there, the tennis ball separates. So the force, as a function of time, is certainly more complicated. But what we typically do when we use the average force approach that we did in that problem, what we're showing is this. The area under the curve equals the impulse. And so if we choose to use an average force, what we're doing is finding the value of F, where if we treat the force as being constant, we get the same area under the curve. So if the areas match, then the impulses match. And that if the impulses match, we'll have the same change in momentum for either situation. Okay, but be aware, in general, when we have collisions, the forces are some function of time, more likely than being a constant force. So again, momentum conservation says we don't have to know the details of what happened in the collision. We just have to know what was going on before masses and velocities, and we can relate those to masses and velocities that happen afterwards. So let's see. We've said that in all of these examples that we look at, in collisions in particular, momentum is always going to be conserved in all of those collisions that we look at. Now, the question becomes, well, is kinetic energy conserved? Will kinetic energy be conserved in a collision? And maybe, maybe not. So we've looked at examples. Let's take a look here. We've got these two objects coming together. We've got a certain amount of momentum here and here. They're in opposite directions, so we've got to do vector addition and find out if there's any net momentum. Maybe there's zero momentum. But they collide. Here's the collision, and here they are separating. Now, if the definition of elastic is that the relative speed of approach matches the relative speed of separation. So if a collision is elastic in nature, then again, whatever speed of approach we had matches the speed of separation. If we do have a collision that's elastic, then what we find is that the kinetic energy is conserved. So it kind of makes sense. Let's see. Let's say A and B come in. A has some kinetic energy. B has some kinetic energy. We add those together to get the total amount. They collide and they separate with the same relative speed. Now, not the individually. They don't have to have the same individual speeds. In fact, you can see their directions have changed. But the kinetic energy here and the kinetic energy here combined will equal the total kinetic energy here if the collision is elastic. Now, if it's less than elastic, then we begin to say that it's inelastic. If it's not perfectly elastic, then it's something short of that. And then we have completely inelastic, where there's no speed of separation at all. So the speed of separation can match the speed of approach. That would be completely elastic. It can be less than the speed of approach. That would be inelastic, and there's a range of inelastic here. And then there can be completely inelastic where the speed of separation is 0. Okay. Is there a way they could separate at higher speeds than what they approached at? That would be like an explosive collision, right? Where you've got some little springs inside there that are all ready to push back, and when the collision happens, the springs push away extra forcefully, or maybe there's a little chemical reaction that takes place and pushes. So you could still conserve momentum even if during the collision some kind of explosion takes place or some spring energy is released. You still have momentum conservation. All right, here we go. We're going to try and come up with some formulas, I think, yeah. Okay, we got two objects colliding elastically. Now, I think they've done the right thing here. What they've done is they've shown both objects going in this direction. And the reason why is when we're doing these derivations, it's hard to think about what did the negative velocities indicate. And so I think it's good that they've written them both kind of in the forward direction. It's easier for me to think about. And then here they are after the collision. Now notice A comes in going faster, but A comes out going slower. B is going slower at first, but then after the collision it's going faster. If the collision is elastic, then here are the formulas we would have to work with. So if it's, here are the two coming in. Now, they've used V1 and V2 for the initial speeds, and V1 prime and V2 prime. I am going to try using U1 and U2. I have a harder time with primes, and that's because, look down here, we're going to have squares of these. It just becomes too many subscripts and superscripts. So if I have primes here, just handwritten, I confuse myself. So I'm going to use, and I hope this is okay, I'm going to use little u's for the initial velocities. So I got this from a textbook, and it was easier for me to work with using u's and v's. So anyway, u and u1 and u2, and then after v1 and v2. So momentum conservation says this. It says m1 times u1 plus m2 times u2 equals m1 v1 plus m2 v2. That's one dimension so far. We're not looking at angles or anything. And then the kinetic energy formula would say that the kinetic energy, 1/2 mv squared plus 1/2 mv squared, 1/2 mv squared, 1/2 mv squared, except those guys are u's instead of v's. All right, how are we going to solve these? Now, what we can do is we can take the first equation, and what I'm going to do is I'm going to take the terms that have m1 and put them on the left side, and then I'm going to take the terms that have m2 and put them on the right, and then for kinetic energy I'm going to do the same. So that's what those last two formulas, this is the momentum formula, and this is the kinetic energy formula with everything rearranged. Now the way these problems usually work is this. It's in the homework it'll say something like, we have two objects, they have m1 is 5 kilograms and m2 is 7 kilograms, and the initial speeds are 11 meters per second and 17 meters per second. Find the final speeds. So that's kind of how this works. Now, remember with the inelastic collision, the perfectly inelastics, those were great because there was only one speed to calculate. Here we've got two speeds to calculate. Now, we have two equations though. So instead of one equation, one unknown, we have two equations, two unknowns, and the algebra is not trivial. I think I still remember this. It was so traumatic. Back in my freshman year in college, learning about elastic collisions and kinetic energy and momentum, and then going in and trying to solve formulas to find out what the final velocities would be. And I was just so optimistic because I looked at those two equations and I go, they aren't hard. I can get through those right away. And I had a hard time getting through that derivation. Again, it was so traumatic, I still remember it. But here's a trick. So I learned a trick years later. Instead of just trying to do some kind of direct substitution, what you can do is you can take the kinetic energy formula, which has all the squares in it, which are terrifying, and divide it through by the momentum equation. So that's what I'm going to do on the next page, and that's where we're going to pick this up. So if you remember from the previous slide, the kinetic energies are on top, the momentum are down below, the momentum equation is, and what we can do then is the M1s cancel out and the M2s cancel out, and we end up with, well, a couple of other things happen. This is the difference between two squares, right? So that's going to be U1 minus V1 times U1 plus V1. Well, the U1 minus V1 goes away. And on this side, again, the M2s cancel, difference of two squares, the V2 minus U2 term cancels, and this is all we're left with. Now, we haven't really completely solved the equation, but we have determined something very, very important. When we rearrange these guys, what we get is U1 minus U2 is equal to V2 minus V1. What is U1 minus U2? And that's the relative speed of approach. Remember, U1 was going faster, or U1 was a higher speed, and U2 was slower. And then at the end, V2 is higher and V1 is slower. So if the difference of the initial speeds is 15 meters per second, it says that will also be true at the end. The difference between the velocities, the relative velocity of approach equals the relative velocity of separation. And that's important. Okay, so I'm going to box that because that's an important thing to say. What we've already established is that if kinetic energy is conserved, this will be true, and this is a statement of the collision was perfectly elastic if these two speeds match. All right, so that's what happens in a reaction, in a collision where kinetic energy is conserved. Now, what else could we use with this formula? And what I can do now is, essentially what we've done is we've eliminated the equation that had all the squares in it. All the squared quantities, the v squareds and the u squareds are gone. And so now I have this equation, which incorporates the kinetic energy principles, and I can take that back to the original momentum conservation equation. And what I did was I solved for V2 to eliminate it, plugged it in, and now what I have is a linear equation that does not include V2. V2 is not included in that equation. We've eliminated one of the unknowns. And so I can algebraically solve this. It's still a few steps here, as you can see, but what I've done is I've collected terms with V1 on the left, and then carefully canceled out and simplified the terms on the right. I'm going to turn the page here. And what I ended up with was this. Oh, that was a big jump. Let's go back. So what I've got is, before we go to the next page, what I have is M1 plus M2 times V1 is equal to M1 minus M2 U1 plus 2M2 U2. Now U1 and U2 were the initial speeds. Those were given. And the masses were all given. The only thing left for me to do is take this M1 plus M2 and divide it through the other side. So that's what I did. Now, once I've solved for V1, then I could go back and solve for V2. Or what I could do is I could just stare at the equation I had for V1 and switch all the ones and twos. So the momentum conservation, it can't be based on which object we called 1 and which object we called 2. We just arbitrarily assign those numbers. And so once I've got a solution for V1, I can take every 1 in here. So there's a 1. I'll change that to a 2. I'm going to change that to a 2. I'm going to change that to a 1. Oh, that didn't change then. This is going to be a 2. This is going to be a 1. So I can switch all the 1s for 2s, and I can get the other equation. Okay, it's got to be the case that I can switch the 1s and 2s, and the equations work the same way. So that's it. So that's a formula that works. It's one-dimensional, It's an elastic collision, kinetic energy is conserved, and if someone tells me the initial speeds and the masses, I can figure out what the final speeds would be. Okay, so that's a formula you can come back to and use in some of these problems, but this is an interesting derivation. Now, what would happen if, let's look at a particular example, what would happen if object 2 starts out at rest? What if it starts out not moving at all? Well, if the second object is at rest, those terms drop off, and it simplifies to this. Now, if you have something just sitting there at rest and you run into it, what are the possible speeds at which you could be coming out of that collision? Very quickly here, I guess it's time to wrap stuff up, so I'll do that and then we'll come back and pick up here. If M1 is much, much bigger than M2, so what would that mean? We have a very low mass object and we have a really high mass object coming, just barreling down on this low mass object. And what it says is if M1 is really, really big, we can just ignore the M2s in the limit where M1 is much, much bigger. Well, that says that the big object never slows down in the limit where its mass is so much bigger. This is like, the semi-truck running into a mosquito along the freeway. So the mosquito's just right there and the truck comes and hits it. Well, the truck doesn't slow down. Now if the mosquito, I know the mosquito's going to end up splattered on the windshield, but what happens if the mosquito somehow bounces off the truck instead? What if the object is pushed away from the truck? How fast would that be? And if it's an elastic collision, then the speed coming off is twice the speed of the truck. So if the truck's going 50 miles an hour, the object bounced off of the truck when it hits would come off at 100 miles an hour. Okay. You could think of this, I guess, as an automobile accident where a car runs into a pedestrian. So if the car is going 20 meters per second and the pedestrian is hit, and elastically, if it's an elastic collision, then the speed at which the pedestrian would be flying out of that collision would be twice the speed. It'd be 40 meters per second. Okay, so momentum conservation makes those predictions. And then what happens in the other extreme? What happens if you have something that's got a lot of mass that's just sitting there at rest, and something with very, very little mass comes in and runs into it? If it's elastic, then what that low mass object does is it bounces off and comes right back off at the same speed in the opposite direction. Well, that would be elastic, right? That's like the brick wall approximation, where you have a rubber ball and it comes in and it hits a brick wall. Well, how much does the brick wall move? Doesn't. And so the ball comes right back off at the same speed it went in with, whereas the brick wall is unaffected. It just remains at rest. So we'll stop right there. I think we're out of time. And so any questions? Stop by office hours.